Hello learners, welcome to our chemistry course at senior secondary level. We will discuss lesson number 2, atomic structure of your chemistry course. You will learn about the internal structure of an atom, which will help you to understand the correlations between its structure and properties. Dr. Sunita Bansal, Assistant Professor, ARSD College, University of Delhi, will explain topics related to atomic structure.
Today we discuss lesson 2 of module 2 of your dispatch, atomic structure. As you know, everything is made up of atom, so understanding atom is very important. Dear learner, as you know, chemistry is the study of matter, that is, things we see around us includes everything. As we keep on dividing matter, we will reach to our atom. John Dalton revived the concept of atom in the beginning of 19th century and termed it as atomic theory. Later on, experiments also proved this fact. Dalton's theory: all matter are composed of atom. All atoms of a given element are identical. Atoms cannot be cut, indivisible and indestructible. Now, let us start our journey of atomic structure from the discovery of fundamental particles, electron, proton and neutron. You can see on your slide that the fundamental particle, electron, is represented by the symbol E and its mass is in the power of 10 to the power minus 31 kg, and the charge is negative. For the proton, symbol is P, size is much higher than the size of electron. It is almost 1840 times, and the charge is exactly opposite to the electron charge. This is -1, this is +1. The electron was discovered by J.J. Thomson in year 1897. Yes, atom has electron and proton as two identity, but there is one more identity, that is neutron, which carry no charge. But this is electron and protons are responsible for the whole mass of an atom. Learner, after understanding about the constituents of particle of an atom, electron, proton and neutron, let us understand the concept of atomic number, mass number, isotopes and isobars. Atomic number, as you can see on the slide also, atomic number is the number of proton in an atom. This is equal to the number of electron in an atom. So, atomic number is the number of proton or the number of electron in an atom. What is the mass number? Mass number is also called atomic mass, represented by A. It is the total number of protons and the neutron in an atom. This is the representation of an element. X is your element symbol. Suppose we are talking about fluorine, it will be represented by F. A is the mass number and Z is the atomic number of an element. Now we take an example of fluorine for calculation of neutron. Number of neutron in an element is the mass number minus atomic number. Neutrons is equal to A minus Z. So, for a particular element fluorine, mass number of fluorine is 19, atomic number of fluorine is 9. So, you can calculate the number of neutrons. 19 minus 9, it is 10. Dear learner, now you are able to calculate the number of electron, proton and neutron in an atom from their atomic number and atomic mass. Atoms of a given element not necessarily have the same mass. Most elements have two or more isotopes, atoms that have the same atomic number but different mass number. Let us take the example of isotopes of hydrogens. Hydrogen has three isotopes: hydrogen, deuterium, tritium. Hydrogen contains no neutron, deuterium contains one neutron, and tritium contains two neutrons. Uranium has two isotopes. Isotopes have same atomic mass but different atomic number. Different isotopes have lot of difference in their properties. Here the first isotope of uranium used in the nuclear reactor and atomic bombs, where the second isotope like the properties necessary for these applications. Now, after understanding about the constituents of atom, now try to understand the structure of atom. For that, we discuss here number of models which have been proposed for the internal structure of the atom. The first attempt to describe the structure of atom is termed the model by the J.J. Thomson. On the basis of his experiment on the discharge tubes, Thomson proposed a Thomson watermelon model. Here in this model, atom is largely positively charged bodies with number of small negatively charged electrons scattered here and there. You can see, learners, that electrons are scattered here and there like a seeds in the watermelon, and the positive charge is like a plum. It's like a plum, and so we also call it plum pudding model. Next we come to the Rutherford's experiment. Rutherford's experiment is based upon the gold foil experiment. In this experiment, a beam of fast moving alpha particle positively charged helium atom was passed through a thin foil of gold. Particles are detected on the circular path. This is a circular photographic plate. You can see on the screen, this is a circular photographic plate. Let me come to the results. You can see mostly rays pass through the foil. Some of them deflected slightly. Some are deflected to the small angle. Some are deflected to the large angle. And rebound of the rays is very, very less. So we can draw the conclusion. What is the conclusion? This is the conclusion. Dense and positively charged region at the center of the atom is called nucleus, and most of its mass contained in this nucleus. Rest of the atom, empty space, contained much smaller negatively charged electron in this circular path. But there is a drawback of this model. By Maxwell theory, a charged particle undergoing acceleration emits radiation. As a result of electron moving around the nucleus, would approach the nucleus by the spiral path. You can see in the picture also, and thus collapse. It does not happen with the atom. Atom is stable. So we can say the Rutherford models failed to explain the stability of an atom. The next attempt to suggest a model for the atom was made by Niels Bohr. This model used the concept of quantization of energy of electron in the atom. Since this fact was suggested by the line spectrum of hydrogen atom, it is better to understand the meaning of spectrum. For this, we begin with the understanding of nature of an electromagnetic radiation. Electromagnetic radiation is a kind of energy which is transmitted through a space in the form of electric and magnetic field as shown here. You can see the beautiful picture of electromagnetic radiation on your screen. This is the direction of propagation of wave, and the electric field component and the magnetic field component, they are perpendicular to each other. It is quite visible here in the picture. Now we discuss the parameter of electromagnetic radiation related to this picture. First we discuss amplitude. Amplitude is the maximum height to which the wave oscillates. This is a wave and this is a maximum distance to which wave may oscillate. The wavelength is the distance between the two wave crest or trough. I think you understood from the picture what is crest and trough. Crest is the maximum height in the upper side and trough is the maximum height in the negative axis. Frequency is the number of wave or crest that pass through a given per second, and wave number is the number of waves per unit length. Velocity, or distance traveled by a wave in 1 second. These are related by these equations. This is a frequency which is related to velocity of light and the wavelength. This is the wave number which is inversely proportional to the wavelength. And the velocity of light, learners, it is 3.0 10 to the power 8 meter per second. Depending upon the characteristics like wavelength, frequency and wave number, electromagnetic radiations are of many types and constitute a electromagnetic spectrum. You can see the beautiful picture of electromagnetic spectrum. It may lie in any region, gamma ray region, X-ray region, ultraviolet region. It is a visible region, infrared region or a radio wave region. The wavelengths are quoted here. We the people only can see in the visible length. So we go in the detail of this spectrum. The spectrum is obtained when a beam of light passes through a prism. We get a range of color from the violet to red. That is Vivgyor, the color of rainbow. And it is obtained as a continuous spectra. You can see the white light is passed through a prism and the 7 color of rainbow is obtained. And this is your, what is this? This is your continuous spectra. We come to the next spectra, that is the line spectra. Here we only discuss the hydrogen atom spectra. It is obtained when electric discharge is passed through a tube containing hydrogen gas which emit light, and this is passed through a prism. Then it splits up to set of 5 lines. These lines are Lyman series, Balmer series, Pershing series, Brackett series, Pifune series. You can see how we are getting these lines of spectrum. Yes, when we jump from second energy level to the first, third energy level to first, fourth energy level to first. That is, if we are jumping from higher energy level to the first energy level, we get the Lyman series. Similarly, Balmer series is obtained when we jump from higher energy level to the second series, and same way for the Pershing, Brackett and Pifune series. After understanding the concept of spectrum of hydrogen atom on which Bohr model is based, we come to the Bohr model. In Bohr model, electrons move around the nucleus in a circular path which is known as orbit. You can see here also. This Bohr's model is based upon the postulates which is known as Bohr's postulate. Electrons move in a definite circular path around their nucleus is orbit. Electrons can change the orbit by absorbing or releasing energy. E is equal to h nu, that is EF minus EI. EF is the final energy and EI is the initial energy. Angular momentum of an electron is always the integral multiple of h upon 2 pi. Let's now move to the other concept. As you know, light is both wave-like and particle-like. That some of the properties of light, for example, diffraction and interference, can be explained on the basis of its wave nature. On the other hand, some other properties like photoelectric effect and scattering of light can be explained only on the basis of particle nature of light. Thus, light has a dual nature, possessing the properties of both wave and a particle. That is, light could under some condition behave like a particle and under some other condition it behave like a wave. In 1923, a young French physicist, Louis de Broglie, argued that if light can show wave as well as particle nature, he combined both the concept mathematically and derived the de Broglie relation. An important consequence of the wave-particle duality of matter and radiation was discovered by Werner Heisenberg in 1927, and it is called the uncertainty principle. The uncertainty principle showed that it is impossible to take any measurement of object without disturbing the object. He tried to locate electron by bombarding them with the photon of light. But once the electron is hit, it moves to a new location with new speed. In the other words, act of observing the electron produce a significant, unavoidable uncertainty in the position and the motion of electron. That means it is fundamentally impossible to know precisely both the velocity and the position, of a particle at the same time. Mathematically, he combined these two things and it come out to be like this. Mathematically, uncertainty in position and momentum is always greater than or equal to h upon 4 pi. This is what the Heisenberg uncertainty principle. Wave mechanical model of atom was proposed by Erwin Schrödinger, which is based on some postulate that have no foundation in classical physics. This model, the motion of electron inside the atom, could be described in the terms of mathematical function called wave function. The wave function are assumed to contain all information about the electron and are obtained by the solving Schrödinger wave equation. The square of wave function is measure of probability of finding an electron in a three-dimensional space around the nucleus. On solving the Schrödinger wave equation for hydrogen atom, we get a number of wave function which are characterized by three quantum number, say principal quantum number, azimuthal quantum number, magnetic quantum number. There is another quantum number we will discuss later on. These quantum numbers arise in the process of logically solving the wave equation. Every electron in an atom has unique set of quantum numbers which help to describe the three-dimensional region where there is a maximum probability of finding the electron. The region is called an atomic orbital or simply orbital. The principal quantum number, symbol is N, describe the energy in principal shell of an electron within the atom. N can have only positive non-zero integer value. This means that in an atom, the electron can have only certain energies. Thus, we may say that N quantizes energy of an electron. The principal quantum number also determines the mean distance of the electron from the nucleus, that is its size. Greater the value of N, farther the electron from the nucleus. Azimuthal quantum number, the value of L may be 0, positive, integer, less than or equal to N minus 1. As you know, N is the principal quantum number. The L can be 0, 1, 2, 3 up to N minus 1. Different values of L correspond to different types of subshells, and each subshells contains orbital of a given shape. For L is equal to 0 correspond to S subshell and contains the orbital with spherical shape called S orbital. L is equal to 1 correspond to P subshell and contains the orbitals with a dumbbell shape called a p orbital. There are 3 p orbitals in each p subshell. For L is equal to 2 correspond to d subshell and contain the orbital with clover leaf shape called d orbitals. The quantum number symbol ml describes the direction or orientation of the orbital in a space. Quantum number ml may have any integer value from minus L to plus L. For example, here you can see also for L is equal to 2, ml can have the values minus 2, minus 1, 0 and 1 and 2. The magnetic spin quantum number ms describes the spin of an electron, whether it is clockwise or anticlockwise. The quantum number ms does not arise while solving Schrodinger equation. The clockwise and anticlockwise direction of electron spins has arbitrarily been assigned the value plus half and minus half. Learners, as we have discussed earlier, azimuthal quantum number is responsible for the shape of orbital. It is defined as the three-dimensional region of a space around the nucleus where there is a maximum probability of finding the electron. Now let us try to understand the meaning of orbital by taking example of 1s orbital, which is spherical. A node is a region in a space where the probability of finding the electron is close to 0. You can see in your picture, this is a s orbital, spherical in shape. This is what? P orbital in the x direction. This is in y direction. This is in the z direction. And the space between these two is your nodal planes, where the probability of finding the electron is 0. These are the 5 orbitals shapes for the d orbital. If you talk about the f, there will be a 7 such orbitals. Let us now take up the distribution of electrons in these shells and subshells. Such a distribution of electrons is called electronic configuration and is governed by the 3 basic rules or principles. Aufbau principle. This principle is concerned with the energy of atom and states that electrons occupy orbitals in such a way that the energy of atom is minimum. That is, electron in an atom are filled in increasing order of their energy. You see, first orbital filled is by 1s, then 2s, now 2p, then 3s. Not 3s will be filled first, this 2p is filled first, then 3s, after 3s, 3p, then 4s, then 3d, then 4p, then 5s. This way the ladder can be made for filling the orbitals in energy labels. Now we come to the another principle filling the shells is Pauli exclusion principle. This principle states no two electrons can have all the 4 quantum number to be same. For example, for n is equal to 2 shell, L can be either 0 or 1, ML value can be either 0, -1, +1, and the spin value, spin quantum number must be +half or -half. I mean to say all the 4 quantum number must be different. There is a 2 notation used for filling the configuration. Orbital notation method is used and orbital diagram method is used. In orbital notation method, orbitals which are filled are written in the order of increasing energies. The respective electrons in them are indicated as superscript as shown here. Here we have taken the examples of boron, carbon, nitrogen and oxygen. In the orbital diagram method, the orbitals are represented by circles or boxes. Here we represented boxes and written in the order of increasing energies. The respective electrons are indicated as arrows whose directions represents their spin. Aufo principle helps to determine the electronic configuration of an atom in a periodic table, but in certain cases it fails to predict the correct electronic configuration where the energies of neighboring subshells are quite close. This is due to the extra stability of half-filled or completely filled orbital. It depends upon symmetry of the orbitals and the exchange energy. We know that the symmetry leads to stability, and the stability of half-filled and completely filled orbitals is explained by exchange energy also. Larger the number of electrons with the same spin, larger is the exchange energy. Larger the exchange energy, stable is the electronic configuration. This is given by the Hund's rule, and this rule is said as if number of orbitals of same subshells are available, then electrons distribute in such a way that each orbital is first singly occupied with the same spin. For the example, for nitrogen atom, atomic number is 7. First 1s electron is filled, then 2s orbital is filled and 2p is filled in such a way that it is singly occupied all the subshells. Not like this way. This is a wrong configuration. This is a correct configuration. Learner, I think now you have understood the atomic structure. Thank you.